Alright, here we are for the notes for sound. This will be in two parts. This is the beginning of part one. Sound is the form of energy that spreads out through space. When a singer sings, the vocal cords in the singer's throat vibrate, causing adjacent air molecules to vibrate. A series of ripples in the form of a longitudinal wave travels through the air. Vibrations in the eardrum send rhythmic electrical pulses into your brain, and you hear the voice of the singer. So you never thought all that went on just so you could hear music. All sounds originate in the vibrations of material objects. The thing of vibration is all sound starts with vibrations. So the source of all sound waves is vibration. That's a key concept for this chapter. In a piano, violin, or guitar, a sound wave is produced by vibrating strings. In a saxophone, a reed vibrates. In a flute, a fluttering column of air at the mouthpiece vibrates. Your voice results from the vibration of your vocal cords. So you can see all of these things that produce sound are produced by vibrating objects. In each case, the original vibration stimulates the vibration of something larger or more massive. The sounding board of a stringed instrument, the air column within a reed of a wind instrument, the air in the throat or mouth of a singer. This vibration material then sends a disturbance through the surrounding medium, air, in the form of a longitudinal wave. The frequency of the sound waves produced equals the frequency of the vibrating source. We describe our subjective impression about the frequency of sound by the word pitch. You'll see that this is subjective. A high-pitched sound like that from a piccolo has a high frequency. A low-pitched sound that from a foghorn has a low vibrational frequency. So pitch is subjective to the person hearing it. A young person can normally hear pitches with frequencies from about 20 to 20,000 hertz. As we grow older, our hearing range shrinks, especially at the high frequency end. So you start at 20 hertz to about 20,000 hertz is your range to start out with. And the thing is, as you get older, these both go towards the center. You can't hear as low and you can't hear as high. Sound waves with frequencies below 20 hertz are called infrasonic. That's an infrasonic sound below 20 hertz. Sound waves with frequencies above 20,000 hertz are called ultrasonic. So those are above 20,000 hertz. Humans cannot hear infrasonic or ultrasonic sound waves. Dogs, however, can hear frequencies of 40,000 hertz or more. Bats can hear sounds at over 100,000 hertz. What is the source of all sound? As a source of sound vibrates, a series of compressions and rarefactions travel outward from the source. Clap your hands and you produce a sound pulse that goes out in all directions. Each particle moves back and forth along the direction of the motion of the expanding wave. A compression travels along the spring similar to the way a sound wave travels. As you see, it spreads out here, it comes together there, it spreads back out here, comes together, spreads out, comes together. Here you're getting compression in these areas. Opening and closing a door produces compressions and rarefactions. When the door is open, a compression travels across the room. So you open the door, you see the drapes. When the door is closed, a rarefaction travels across the room. So he pulls the door shut, and now the drapes are being pulled in. When you quickly open a door, you can imagine the door pushing the molecules next to it into the neighbors. The neighboring molecules then push into their neighbors, and so on, like a compression wave moving along a spring. A pulse of compressed air moves from the door to the curtain, pushing the curtain out the window. This pulse of compressed air is called a compression. You may have noticed this when you open the door in one room, it may shut the door in the next room. When you quickly close the door pushes the air molecules out of the room. This produces an area of low pressure next to the door. Nearby molecules move in, leaving a zone of lower pressure behind them. Molecules then move into these regions, resulting in a low pressure pulse from the door to the curtain. This pulse is a low pressure air is called rarefaction, and you might see this also if you close a door. It might pull something shut on the other side of the room. For all wave motion, it is not the medium that travels across the room, but a pulse that travels. In both cases, the pulse travels from the door to the curtain. We know this because in both cases, the curtain moves after the door is opened or closed. On a much smaller but more rapid scale, this is what happens when a tuning fork is struck when a speaker produces music. The vibrations of the tuning fork and the waves it produces are considerably higher in frequency and lower in amplitude than in the case of the swinging door. You don't notice the effect of a sound wave in the curtain, but you are aware of them when they meet your sensitive eardrums. Consider sound waves in a tube. When the prong of a tuning fork next to the tube moves toward the tube, a compression enters the tube. When the prong swings away in the opposite direction, a rarefaction follows the compression. As the source vibrates, a series of compressions and refractions is produced. And we're going to do something in class with this. How does a sound wave travel through air? So sound travels through solids, liquids, and gases. Most sounds you hear are transmitted through the air. Put your ear to a metal fence and have a friend tap it far away. Sound is transmitted louder and faster by the metal than by the air. Click two rocks together underwater while your ear is submerged. You'll hear the clicking sound very clearly. Solids and liquids are generally good conductors of sound. The speed of sound differs in different materials. In general, sound is transmitted faster in liquids than it is in gases, and still faster in solids. Sound cannot travel in a vacuum. The transmission of sound requires a medium. There may be vibrations, but if there is nothing to compress and expand, there can be no sound. Sound can be heard from the ringing bell when air is inside the jar, but not when the air is removed. So in space, there is no sound because there is no medium for the sound to travel through. So what media transmits sound? Solids, liquids, and gases. The speed of sound in a gas depends on the temperature of the gas and the mass of the particles in the gas. The speed of sound in a material depends on the material's elasticity. If you watch a distant person hammering, the sound of the blow takes time to reach your ears, so you see the blow and then you hear it. You hear thunder after you see lightning. These experiences are evident that sound is much slower than light. The speed of sound in dry air at 0 degrees Celsius is about 330 meters per second, or about 1,200 kilometers per hour. This is about 1/1,000,000th of the speed of light. Increased temperatures increase speed slightly. Faster moving molecules bump into each other more often. For each degree increase in air temperature above 0 degrees Celsius, the speed of sound in air increases about 0.60 meters per second. So normally we say at about room temperature, speed will travel at about 340 meters per second. The speed of sound in a gas also depends on the mass of its particles. Lighter particles such as hydrogen molecule and helium atoms move faster and transmit sound more quickly than heavier gases such as oxygen and nitrogen. That's how whenever you put helium in your mouth and you talk, it's making it vibrate faster, and so as the sound goes through the helium, that's why your voice goes really, really high. The speed of sound in a solid material depends not on the material's density, but on its elasticity. Elasticity is the ability of a material to change shape in response to an applied force, and then resume its initial shape. Steel, you would imagine, is very elastic because it's basically staying in that shape. Putty would be inelastic. Sound travels about 15 times faster in steel than in air, and about 4 times faster in water than in air. How far away is a storm if you note a 3-second delay between a lightning flash and the sound of thunder? For a speed of sound in air of 340 meters per second, the distance is 340 times 3 seconds, so it's about 1,000 meters or 1 kilometer. Time for the light is negligible, so the storm is about 1 kilometer away. What determines the speed of sound in air? Sound intensity is objective and is measured by instruments. Loudness, on the other hand, is a physiological sensation sensed in the brain. The intensity of a sound is proportional to the square of the amplitude of a sound. That's kind of confusing, and we're going to talk more about that when we do problems with this. Loudness, however, differs for different people, although it's related to sound intensity. The unit of intensity for sound is the decibel, or the dB, after Alexander Graham Bell, inventor of the telephone. So we've all heard of the decibel level before. The speaker vibrates in rhythm with an electric signal. The sound set up similar vibrations in the microphone, which are displayed on the screen on an oscilloscope. Starting with 0 at the threshold of normal hearing, an increase of each 10 decibel means that the sound intensity increased by a factor of 10. A sound of 10 decibels is 10 times as intense as a sound of 0 decibels. 20 decibels is not twice, but 10 times as intense as 10 decibels, or it'll be 100 times as intense as something at the threshold of hearing. 60 decibel sound is 100 times as intense as something as 40. So this doesn't go by factors of 2, it goes by factors of 10. So when you go from 0 to 10, it's 10 times stronger. And then if you go from 10 to 20, it will be another 10 times stronger. So if we had 0, 10 decibels, and 20 decibels, so this step means it's 10 times stronger. If I went another 10, it would be 100 times stronger, because 10 times 10 is 100. Here's a list of some average decibel sounds. So you have your decibel levels over here and some common things that you would hear. Hearing damage begins at about 85 decibels. The damage depends on the length of exposure on frequency characteristics. A single burst of sound can produce vibrations intense enough to tear apart the organ of corti, the receptor organ in the inner ear. Less intense but severe noises can interfere with cellular processes in the organ and cause its eventual breakdown. Unfortunately, the cells of the organ do not regenerate. This is how, remind me to talk about this in class, it is how people are starting to lose their hearing much faster these days. Here we go, sound wave traveling through the ear canal vibrates the eardrum, which vibrates 3 tiny bones, which vibrate the fluid-filled cochlea. Inside the cochlea, tiny hair cells convert the pulse into an electrical signal to the brain. Earplugs typically reduce noise by about 30 decibels. What's the difference between sound intensity and loudness? When any object composed of an elastic material is disturbed, it vibrates at its own special set of frequencies, which together form its special sound. Drop a wrench and a baseball bat on the floor and you hear distinctively different sounds. Objects vibrate differently when they strike the floor. We speak of an object's natural frequency, the frequency at which an object vibrates when it is disturbed. Every object out there has its own natural frequency. That's why you have tuning forks, and each tuning fork has its own frequency set to it. When it vibrates at that frequency every single time. All objects have that, and it's called their natural frequency. Natural frequencies depend on the elasticity and shape of the object. The natural frequency of the smaller bell is higher than that of the big bell, and it rings at a higher pitch. Most things, planets, atoms, and almost everything in between have a springiness and vibration at one or more natural frequencies. A natural frequency is one at which minimum energy is required to produce forced vibrations, and the least amount of energy is required to continue this vibration. What happens when an elastic material is disturbed? It will vibrate. That's the end of part 1.